Now we saw earlier where we can take a simple function. For instance, let's say it's f of x equals x squared plus 3x plus 6. And we can say find f of 7, for instance. Well, wherever there's an x, we're going to put a 7. So this would be 7 squared plus 3 times 7 plus 6. And of course, this would equal 49 plus 21 plus 6, which equals 76. Okay, that's easy enough. But what if we want to change the whole design of the function? Okay, so for instance, assume we have the same thing, f of x equals x squared plus 3x plus 6. But assume we wanted now to, instead of putting in a number, we wanted to put in a completely separate expression. So we wanted to embed a completely separate expression into this function. So assume we wanted to find, for instance, f of x plus 7, okay? So this is an entirely different expression, okay? So what would this be? Well, again, wherever there's an x, instead of putting in just 7, we're going to put in x plus 7. So that would equal x plus 7 squared plus 3 times x plus 7 plus 6. Now, we never want to leave it in this form, right? We want to try and simplify as much as possible, which means getting rid of these parentheses. So that gives us x squared plus 14x plus 49 plus 3x plus 21 plus 6. Okay, now we're going to combine like terms. That gives us x squared. Okay, that gets rid of that. 14x plus 3x is 17x plus 17x. That gets rid of that term and that term. And then this is 76. Okay, let's try another one. What if we have f of x equals x to the 4th plus 3x squared plus 1? What if we wanted to find, for instance, f of x squared plus 1? Okay, wherever there's an x, we're going to embed x squared plus 1. So we're embedding an expression in for x instead of just a constant. Okay, so this f of x squared plus 1 would equal x squared plus 1 to the 4th plus 3 times x squared plus 1 squared plus 1. Okay, now again, we have to combine and simplify, and this is going to get far more tedious. This is what I mentioned earlier. It's not complicated, it's just tedious, because now we've complicated the function quite a bit. Okay, so here we have effectively x squared plus 1 squared times x squared plus 1 squared plus 3 times x to the 4th plus 2x squared plus 1 plus 1. So all I did was just FOIL that out. Now, okay, so now I know what x squared plus 1 squared is. I can just repeat those here. So this equals then, this equals x to the 4th plus 2x squared plus 1 times x to the 4th plus 2x squared plus 1 plus 3x to the 4th plus 6x squared plus 3 plus 1. We're not done yet. This is not simplified yet. Now we need to simplify it by FOILing this out. That equals x to the 8th plus 2x to the 6th plus x to the fourth plus, okay, so that was multiplying x to the fourth through this. Now I'm going to multiply 2x squared through this plus 2x to the sixth plus 4x to the fourth plus 2x squared. That completes my 2x squared distribution. Now I'm going to distribute the 1 through plus x to the fourth plus 2x squared plus 1. Okay, now I have to add that on to the end. Plus 3x to the fourth plus 6x squared plus 4, adding the 3 and 1 together. So now we can combine like terms and fully simplify. So we've got x to the 8th. It's by itself. It's the only power of 8 that we have. So we can just write that. That's done. Okay. The next highest power we have is x to the 6th. Then we have 2x to the 6th plus 2x to the 6th equals 4x to the 6th. Now we have x to the 4th. So we have 1x to the 4th, 5x to the 4th, 6x to the 4th, 9x to the 4th, plus 9x to the 4th. It gets rid of that, and that. Now we have x squared. So that would be plus 2, 4, 10, x squared. Plus 1, plus 4, that would be plus 5. Now we're fully simplified. But you can see how we can change. You know, we started with this, okay? And now by embedding a relatively simple expression, excuse me, I'm sorry, we didn't start with that. We started with this. But by embedding a relatively simple expression, x squared plus 1, into this function, we end up with something far more complicated. But it also shows the flexibility of using functions for mathematics instead of just expressions and equations. Now we can also take a general function such as g of x equals 3x squared plus x plus 1/2, for instance. And let's complicate this. Let's just stick with this for now. We can also change what x is, okay? So assume that we wanted to find g of t plus 1. So for instance, assume that x can be whatever it wants to be, okay? So it can be any variable it wants to be, but assume specifically we want to use this function to evaluate some time period or some dynamic over time. Then we could effectively replace x with t, okay? And now let's assume we want to not just evaluate t, but we want to evaluate today and tomorrow. So we want to evaluate this function tomorrow, okay? So that would be t plus 1. Some time period t, today, plus 1, which would be tomorrow. We can do that with functions. So if we want to find g of t plus 1, we're just going to put a t plus 1 where there is an x. So g of t plus 1 equals 3 times t plus 1 squared plus t plus 1 plus 1/2. This equals 3 times t squared plus 2t plus 1 plus t, plus, let me white that out, plus t plus 1 plus 1/2 is 3/2. So this equals 3t squared plus 6t plus 3 plus t plus 3/2. Okay, so simplified, g of t plus 1, given that function there, that primary function, this would be g of t plus 1 equals 3t squared plus 7t plus 9/2. Okay, so we can actually change what we want to look at given the function that we want to use.